Alright, so welcome to the second CAD challenge, which will be creating a complete drivetrain. And so first of all, I'm just going to go over a couple of things from the last one. So in the gearbox assembly video, originally I was planning on using a 22 tooth gear. You know, if you look on the JVN calculator, well, these numbers are different from that original one, but I was supposed to use a 22 tooth, but in the video I used a 20 tooth, so that was an error. It's the same thing in terms of how you assemble the gear, but if you look closely, right, you can see how far apart the gears are because it's, you know, two smaller. And you know, if you compare that to these gears over here, you can see they're far closer, and so they will work properly. So make sure that error was addressed. I need to make sure that was the case. And then also with the gearbox, you know, the idea with these CAD challenges isn't just here's how you CAD a gearbox, go do this, right? The idea is also sort of showing the design process and the decision making process behind, you know, we're going to use these motors, these gears, and this sort of layout. And that's really important because that's the key, right? Because every year is not going to be the same, every robot's not going to be the same, and so it's really important to understand how you make these decisions so that no matter what the rules are, what the robot looks like, you can make a gearbox without having to think, oh, I only know how to make one kind of gearbox. And so what we're going to be doing is, with this CAD challenge, sending out a set of restrictions that's different from the video. So, you know, in the original gearbox video, I was like, okay, we'll use a 4-inch wheel, Falcon motors, you know, and we'll use these set of gears and aim for this speed with this current draw, right, and with this robot weight. What we can do now is say, so whoever is doing the CAD challenge, right, when you make your own gearbox, try making it with 6-inch wheels, right, so that changes up things. Now you have to think about, oh, how do I make sure I don't pull too much current, I'm going the right speed? Using a different robot weight, you know, potentially a lighter robot, so that mixes things up. So we're gonna add those restrictions so that you can go off of them and think about your gearbox or whatever the CAD challenge is on your own, and not just here's what the video did, I'm just gonna do that same thing. Because it's important to learn how to make these specific parts, but it's also even more important to learn how they're designed and how you make the decisions around them. So without further ado, let's go on to the drivetrain. And so if you look on the drivetrain, right, we've got the gearbox. In CAD trainings, we went over making 2x1s, gussets, belly pans, all of that, right? So it's really, all we have to do is put it together, add wheels to it, as well as bumpers and bumper rails, right? So I have another video that covers how to make bumpers, so you can watch that to learn how to make them. Quickly want to go over how bumpers are used and how we assemble them if you haven't seen it on the robot, like in competition. Basically, we have a bumpers, which are, you know, like the bumpers on the back side, there's like a 3/4 inch plywood that we use, and then on the front we put pool noodles. That's basically allows us to like ram the robot into another robot and have that squishy like front so that we don't damage any of the parts of the robot. And it's covered with a fabric, right? So that's usually blue or red because alliance colors. And then we paint the bumper, right? So that's the bumper. And then what we do is we have these L-shaped brackets that are 1/8 inch thick, and what we do is we use wood screws to screw them onto the plywood, right? So this whole thing is our bumper, and what we do is when we put it on the robot, we just slide it over the robot. And if you look here, these brackets have a hole on the top of them, and these screws here go on top, and you just use our hands to tighten these so that the bumper stays on the robot during the match, it doesn't flop around. So in terms of a drivetrain, what you need to plan for is adding like a rail of some sort so that you can screw these screws on. And the biggest, it's not hard to add this on, you know, you can see it's just a simple rail. The only thing you have to think about is where the rest of the stuff in the robot goes. So for this year, for example, our elevator was supposed to be the width of the robot, and so the space on these sides here was pretty limited. So that's why we went with a, you know, front and back bumper rail sort of system, right? And that's what we did there. So let's cut the talking and start CADing. So I'll have my gearbox here. I'll just use this one. And in the JVN calculation for that gearbox, we used 4-inch wheels. So I'm going to be making a gearbox and a drivetrain with 4-inch wheels. Obviously, if you're making one with 6-inch wheels, it will look slightly different, or the drivetrain will be a little bit taller, basically. So let's start with an assembly right here. Now I'm not going to be making each 2x1 like one by one because you guys already know how to make them. I'm just going to use my template for a 2x1. I'll have a video for how to make these 2x1 templates as well. So I'm going to select here where I want to put this. So we'll go here. Let's say WCD 2-1. I'll just name it that. Alright, that looks good. Okay. And so the way I've set up my template is basically it creates this form. It's called form. And you can select settings here. So I want a 2x1 and I want it to be so the length and the width of your drivetrain, right? That depends on each game and the robot. So, you know, typically, so the rules have a restriction on the frame perimeter. Basically, that means all these 2x1s that we make for the drivetrain, right? They have a perimeter around them, like the rectangular frame itself, and that has to be a maximum. That can be a maximum 120 inches from previous year's games. And so basically, that means if you have a drivetrain that's 30 by 30 inches square, right? That means you have a 120-inch perimeter of your rectangle, and that's the biggest size you can have. And you know all the configurations in between. And so generally you want to try to stay away from the maximum size because that's a really big robot, and the bigger your robot is, the less space you have to, you know, juke another robot that's trying to defend against you. It makes everything heavier and bigger. So try staying not away from that maximum limit. And then if you have a smaller robot, obviously it gives you less space to mount things and it can be harder to work with. So keep that in mind. For this example, I'm just going to do a drivetrain that's 26 inches long by 24 inches wide, right? So I'm going to make my side pieces, and I'll make these 24 inches long, and we want it to be 1/8 inch thickness because drivetrain 2x1s need to be strong. We're going to use standard 5/32 holes because that's the rivets we're going to be using, and I'm not going to change the colors, and I don't need to change anything else, so we'll hit OK. And what it does is it just creates a 2x1 with that standard hole pattern, and I'm good to go. So I don't need to spend my time making a rectangle, you know, so making that rectangle, another rectangle, and then doing all the holes along the 2x1. Right. So there's our 2x1 on the side, and it grounded it. I don't want it to be grounded, so we'll just move that across. Control C and Control V, so we have a second 2x1. Right, and I made these 24 inches. Oh, so actually I can just use these for my horizontal ones as well, but I'll make new ones. That's because if you look here, right, we have it sort of like an I shape. So these side 2x1s are here, and then I have these other ones on top. So my overall length is the length of this 2x1 plus 2 inches, right? Because 1 inch here and 1 inch over here. So if I want to make a 26 by 24 drivetrain, and these are 24, I already have my 26-inch length, and I can just reuse these for this side. But we will not do that in CAD because we need to add bearing holes on these ones and not on the other ones. So we'll make a second set of 2x1s. Right, and then you want to name this WCD22. Hit OK. And then let's make this 2x1, so again 24 inches. Everything else looks good, so we'll hit OK. There it is. And so as you can see, they're all in line right now. What I'm going to do is go on top view and take this one, and if you do right click, free rotate, so you can basically rotate the 2x1. This is not going to do anything in terms of like constraining it or anything, but I just like to have it in the right place so that it looks, I can visually see how they're going to go together. And I just did Control C and Control V to get that second one. Right, so they're all there. Let's start constraining them. So constrain, I'll just get them on the same height first. So we'll do flush. like that. We'll do another flush like that over here. And oh, wrong one. We'll do a flush right there. And the final one here. Oh, we still really actually need to do it because all these three are flush against each other, so I don't need to do one over here. Right, so that looks pretty good. Alright, that's how we want it to go together. And so I'm going to just do constrain that face over here attached to this 2x1 face right there. Alright, so they're attached. Apply. And we'll do the same thing over here. There we go. If you see, it only attached this 2x1, not that other one, so it can still move around. For that, I'm just going to use the planes. Right, so constrain. And if you're confused about planes, they're basically like, imagine basically having another face in the middle of the 2x1, and they're useful because they're in the middle, and you know you can use them for these kind of constraints, and you don't always have access to faces everywhere, so they're useful in that regard. Right, so my whole assembly right now can move around, so we'll take care of that using more planes. So there's the middle of my assembly, and there's the middle of my 2x1s there. So we hit that, and there you go. Hit apply. Let's see. In that direction, there's the middle, and then you want to use the second 2x1s here. And there we go. Let's try flush. There we go. Hit apply. So now my whole assembly should only move up and down. Yep. And the 2x1s can move, but that's okay. So we'll do another constrain. So right, this is the XZ plane. It's the up and down. And we can just use whichever 2x1 we want. So there we go. Let's try a flush. There it is. So now my whole assembly shouldn't move around. Yep. It's the equivalent of making it grounded, but I like this way more. And then we're going to do these constraints here. So we want these faces to be flush with an offset of 2 inches. Alright. And these 2 inches, the reason why we're doing 2 inches is basically want to have the wheels in that space. And so the wheels take up, you know, almost 2 inches, not quite, but if you have 2 inches, it's like a whole number, and so it makes these gussets simpler. And you know, it's easier to line up things and assemble things. You can also add these kind of 2x1s here if it's 2 inches, so we just want to do that. You could go with a smaller gap technically, but it can make things harder when you're trying to assemble, and it's harder to add other stuff on the side. So do the same thing here, 2 inches, hit apply. Right, so we have our basic frame that we made in CAD trainings as well. And so what we're going to do now is I'm going to save the file just to make sure, in case Inventor wants to crash. WCD, save it, hit OK. And there it is, it's saved. So we'll now place our gearbox. There it is, gearbox, hit open. And I'm just going to rotate it to be that way. There we go. Right, so let's place our gearbox, except we need holes here to place it and add our bearing holes and everything. So in order to do that, let's edit this 2x1. So we can double click, and that will open it inside the assembly, so you don't have to open it separately. And what I want to do is create a new sketch over here. Right, so let's make our hole. So the center hole is pretty simple. It's going to be in the center, and it's a bearing hole, so we'll make it 1.125 inches. There it is. And then we need 2 more, so we'll make 2 more circles here and 1 here. Right, we want them to be equal to each other, so we'll do equal. And horizontally they're the same level, right? So we can do this. So that they're on the same horizontal level, right? That should make sense. And then, oh yeah, and then they're both symmetric about the middle. So So what I'm going to do is I'm going to make a line in the middle like that, and we'll make the line be vertical, and then we'll make it symmetric. So if you're going to use a symmetric constraint in sketches, what you want to do is select your two geometries, so my first circle, my second circle, and then you select the line in the middle, right? So if I select this line, they'll both be symmetric, and so they'll both copy the other side. So this one's going to behave the same way as that one. This way it just removes extra constraints. And then I want to make this line construction because I don't really care about it, right? And then, so the next thing we want to make it equal because these are also bearing holes. So we'll do that. All right. The final thing is how far apart they are. And so I want to go over something here. When you do dimension, right, there's multiple ways you can dimension anything. So if I have these two circles here and I select their centers, I can do this dimension here, right? And that's the horizontal distance from this circle to that circle. It's not the same as another dimension I could do, which is the diagonal distance, right? This is, if you look here, you know how when you scroll down, this dimension pops up like the preview, but if you go in this middle area, there's nothing really except this little symbol over here that you can see. And when you press in this middle area, you get this dimension. And if you see, that's different. That's the center to center distance. And when you're doing drivetrains, and really anything that involves gears or chain or anything, this is a distance you care about, the center to center distance, right? And you don't care about this horizontal one. So it's really important to make sure that when you're doing a drivetrain or anything with chain or gears or belts, that you get these center to center dimensions. And right now it's easy to make it, but when you put the other circle really close to this, like in terms of its height, you can see if I do dimension over here, it gives me the option to do a diagonal dimension, a center to center dimension. But if I go just a little bit above, it's a horizontal dimension. So make sure that you set a center to center dimension, not horizontal one. And a way, if it's difficult for you to do this, what you can do is just move the circle up a lot. This way it's super simple. So you just click the two circles, go somewhere in the middle, hit dimension. I'm going to create a random dimension right now, and then you can do this other dimension that we have over here, which should be 1/8 of an inch. You can change this around on the during the season if you find that the robot's really tippy, or if it's not tippy enough. Tippy enough as in it doesn't turn well. So we have this, we need to change this distance, right? So this is where we go back to our bot lambda calculator. I'll put all these links to the JVN calculator and bot lambda in the description, but basically it's a chain calculator, and I think we went over this in CAD trainings, but I'll just reiterate it. Basically it's to find the distance between these two circles here, so that we can put a nice chain loop around it and not have to add any extra things to our chain to make it fit. We want to have a perfect center to center distance here. So we're going to use 35 chain. We generally use 25 or 35 chain. 25 is smaller, and so it fits in smaller spaces, but it's also a little bit weaker and it can't always handle all the loads. 35 chain is really, really strong, but it's also bigger and heavier. So you don't want to use 35 chain everywhere, but on the drivetrain it's really secure, and it makes sure that you almost never run into chain problems in the drivetrain in terms of not being able to handle the load. And the chain pitch for 35 chain is 0.375, and generally the smallest 35 chain sprockets are 12 tooth, so we'll do 12 and 12. And then here in the links in chain, we want an even number of links. The reason why we want an even number of links is so that we can connect it together and not have any odd numbers, because what that ends up in is if you have an odd number of links, you have to connect it together using either a half link or a master link, which basically are like, if your chain doesn't fit together, you can make it work, but they're also not as strong as just having an even number of links in your chain. So we'll just use arbitrary, like 60 for example, and you get the center distance. Now during the season, this is where you can add, what you can do is add a circle here, for example, that represents your wheels. So this could be, 4 inches in our case, it could be 6 inches, and you can basically check to see if it, for example, this drivetrain, it's hitting this other 2x1 right now, so I can't use a 6-inch wheel. But thankfully, I'm using a 4-inch wheel, so this will be okay. Right, so that's another way you can make sure that this distance works. And basically, if your wheels are further apart, it gives you a more stable base, right? Think of like a limousine. It's really long, so it's very stable, but it's also really hard to turn, just like a limousine, because your wheels are so far apart, your robot takes forever to turn. If you have these wheels closer together, like instead of 9 inches, they're 4 inches apart, they're super close, you can turn very well, but it's also very unstable, and so it's going to be a little bit more tippy. All right, so go back to 9, and then obviously you want to add a little bit of extra distance here. Generally we go like 0.018 or 0.016, and this is basically chain. What happens with chain is as you use a lot of chain and it wears out a little bit, the chain basically becomes a little bit longer than it was initially. And so if you have a loose piece of chain on your drivetrain, it's gonna like hit everything and it can potentially come off, which is something you don't want to have on your drivetrain. So that's why we add this extra distance to make sure that the chain is really taut when we add it to the drivetrain. So we have this. These are our bearing holes done. Now the next thing we need is to mount our gearbox on the center hole, right? And if you remember from our second plate on the gearbox, we added these 4 holes here so that we can attach it to the 2x1s, and we can add those over here. So what we're gonna do is add a circle up here. Let's just do it up here, and we're gonna dimension it. So this circle, what we're gonna do is we're gonna put a 1/4-20 screw through it, right? And we don't want the 1/4-20 screw to thread into it, and we just want it to go through freely. So we're gonna use a 0.257 diameter. I'll put a link to this chart as well in the description, but if you can't remember the screw sizes, like the diameters for the holes, here you can go. You go to this page, and 1/4-20s close fit is 0.257. Right, so back here, 0.257. We'll make it vertical with the center hole and dimension it to be just how we did it on the gearbox second plate, 1.875 divided by 2, because we want a circle with a diameter of 1.875. So we'll have this radius here. Let's do a circular pattern around the center, and we want 6. Hit OK, and then let's select these 2 over here, the top and bottom ones, construction them. So you see these are in the right places now. Right, so that looks good, and we'll finish sketch. We'll hit extrude, and we want to cut. We'll go wrong selection. Okay, we're gonna select everything here and through all, hit OK, and there you go. And you can see obviously this won't work, so we have to go to this pattern here, and let's find. So this is why I like 3D patterns more than doing patterns in Sketch, because it's easier to change stuff in them. So let's find these other holes. There's that one, that one, that one, that one, that one. Right, so you wanna get rid of them, and let's find these ones here. Those 3. Let's go back to the top now. Over here. So that one, and that one. In the middle here, we've got, let's see, these 2 here, it's 5, and then the final 3 here. You could just select like 3 at once and then do it. I just like to select all of them at once, and then right click, suppress, and they're gone. We don't need them. Right, let's return to our assembly. As you can see, there is our bearing hole, and there's the 4 screw holes. That's exactly what we needed, so that's good. Right, so what we're gonna do Now obviously you see inside our gearbox we've got a bearing in here, and so we don't need a bearing on this side of the 2x1, right? So we can just directly attach it. So we'll go constrain, insert, let's do that top screw hole and this one over here. There you go, there you see, there's our gearbox. Hit apply, and then you could technically tilt the gearbox and then insert the other screw hole, but it can be hard to like select it. So I just do constrain, select the hex shaft and the bearing hole we made in the 2x1, and there you go. And this is also a good place in case you catted your screw holes incorrectly or some distances were wrong. You know, Inventor won't let you constrain it, so this is a good place to check. Right, so there's that, and then we can start adding other stuff. So let's add a bearing. And so if you set up your Inventor project, you can see in here in libraries, if you click library, you'll go straight to the parts library. So you don't have to do the whole go back and then do this and then do that. You can just straight click library and you're already there. So we'll go bearings, 1/2 inch hex bearing, place that here. Let's constrain it. So we're gonna select the flange and this bearing hole here. So there we go. There's our bearing. As you can see right now, the hex shaft's too small. Remember in the video we just made this some arbitrary size, and then we'll come back to it in our drivetrain video, and so here it is. We'll have to edit this after we place our wheel. So let's do that. Let's go library, hardware, screws. So first we'll place the screws for our gearbox. So we're gonna measure. So we're gonna go tools, measure distance from this face to the plate over here. As you can see, it's 1.25 inches. You don't have to use measure for that. Like you can see it's 1 inch and a 1/4 inch plate, but I just like to use measure just to make sure. And so we're gonna go assemble, place. Let's go to our library, hardware, screws and nuts, 1/4 inch, 1.20, 1.25 inch socket screw. Open that. Let's place 4 of those. You could do a pattern here, like a circular pattern, but I'm just lazy. I'm just going to insert 4 screws. So select the bottommost part of the screw head, and we'll select our hole here, place that, and let's do that 4 times instead of using a pattern, because why not? And then here we go. And there's our last one. There it is. Hit apply. Okay. So as you can see, we've got our 4 screws here. Now, obviously, if I were to place my wheel here right now, it would hit these screws. So we're gonna have to place some spacers. So we'll go place, library, hardware, spacers. Let's try a 1/2 inch hex spacer. So we'll hit open. There it is. As you can see, there's a 1/2 inch hex spacer. Constrain it, insert, and this part of the bearing, hit apply. There we go. There's our hex spacer.